On behalf of the Computer History Museum, I would like to welcome Professor Arogyaswami Joseph Paulraj for a conversation about his life history. My name is Uday Kapoor, and I am a volunteer in the Oral Histories program at the museum. Professor Paulraj, a former Commodore in the Indian Navy, is currently a Professor Emeritus in the Department of Electrical Engineering at Stanford University. He was born on 14th of April 1944 in Pollachi near Coimbatore, India. He joined the Indian Navy at a very young age and served it with distinction for 30 years. He received his bachelor's degree in electrical engineering from the Naval College of Engineering, Lonavala in India, and his doctorate in electrical engineering from the Indian Institute of Technology, New Delhi. He served in India till 1991, where he pioneered the development of advanced military sonars. He also served as the founding director for 3 major labs in India: Center for Artificial Intelligence and Robotics, Center for Development of Advanced Computing, and Central Research Labs of Bharat Electronics. He is the pioneer of a breakthrough wireless technology known as MIMO, multiple input, multiple output, that he developed at Stanford, which dramatically increases performance and capacity of wireless systems. MIMO is the core technology in the latest Wi-Fi and LTE systems, crucial to local area and mobile wireless communications. Professor Paulraj founded Iospan Wireless Inc. in 1998, which developed the core 4G wireless technology and was later sold to Intel in 2003. And helped it launch its own push into WiMAX. He co-founded BSIM Communications in 2003, which became a leader in 4G chipsets. BSIM was acquired by Broadcom Corporation in 2010. Professor Paulraj was honored with numerous national awards in India, including the Padma Bhushan, Ati Vishisht Seva Medal, and the Vasvik Medal. An IEEE Fellow, Professor Paulraj has been honored with the most prestigious global technology awards, the IEEE Alexander Graham Bell Medal in 2011 and the Marconi Prize in 2014 for his pioneering contributions to the telecommunications industry. So with that, we will start our conversation with Professor Paulraj. Welcome.
Thank you.
I'd like to start with your early life. I know you were born in 1944 in Pollachi near Coimbatore, Tamil Nadu. I guess at that time it was Madras Presidency under the British Raj. It was not an independent country yet. And your parents, I read, Sinappan, Arogyaswami, and Rose. You were one of 6 children. So maybe you can give me your views of your childhood.
Right. So we, Pollachi was a small town in Tamil Nadu, the state of Tamil Nadu. And my father, by the time I sort of became 3 or 4 years old, my father had joined the Indian Navy, which I later followed into. And so he was quite often on transfers, moving around on ships and things like that. So my mother was, and the children were often to give us some stability in education, left behind to. So we spent many years in a town city called Coimbatore, and so I grew up going to school in Coimbatore and in Cochin, and so it's a large family, and but certainly had a very, very happy childhood, and around the age of 11, I finally was sent to a boarding school. Because to avoid me from moving around too much, to give stability in high school. So I was in a school called Montfort School in Yercaud for 4 years, and graduated there in 1959.
So I read that you were always the top student. You always topped the class. That's very nice to know. So the various places that you went to school, like you mentioned Cochin, was probably because your father had to move around,
yes,
being in the Indian Navy. And then I read that you were in a pre-university in 1960 for 6 months. What would that
Right.
refer to?
So it turned out that I finished school in 1959, high school, but it wasn't enough to get into college. I had heard of the IITs, but not really aware of them for some reason. And it wasn't so. In order to get into an IIT, I had to go through another year, which is equivalent to the 12th grade here of a pre-university course. So I joined at a college called Loyola College in Chennai. But turns out at that time, I became aware of the armed forces as a career. My father also felt it was a good one. And so after a few months at Loyola, I joined as a cadet at the National Defense Academy.
So that's usually a very tough exam to get into that, from what I remember.
It was, yes, I think it's fairly competitive. Those days, it was even more competitive than today. But I think I easily qualified. I was a very, very strong student, and so it was unusual for somebody with my profile to join the National Defense Academy, and it was very visible at the academy that I stood out very differently.
And of course, you topped the class.
Right, of course.
This is in Kharagwasla. And you finished your basic training in 1963, I believe.
Right.
And then the fleet basic engineering training from 1964 to 68.
That's correct.
And then you were commissioned in 1965.
Yes, and as a part of my training, I became commissioned in 1965, but continued my training. And much of the training was not the traditional engineering training you would see in a university. It's very much more applied. We were actually exposed to guns and radars and sonars early in our life. So there's more emphasis about that kind of applications than on fundamental theory. But I did learn up theory on my own.
Okay. Yes, I remember reading about some of your comments later about that when you went to IIT Delhi, that you finally went to a real university.
That's correct. And while I think at doing the naval training, didn't have the opportunity of seeing a really good library, and so I would sometimes buy books on my own and read them up. But I should also mention that the Navy recognized those interests of mine and did encourage them. In fact, I was a moment I finished my training, within a few months I was sent off to IIT Delhi to do a master's program.
Right. So we'll come back to that.
Yeah.
So in the 1960s, I understand that the Indian Navy had been experiencing some difficulties with the sonar, especially with the 170B sonar performance. And I understand, and this we can spend some more time a little bit later as well, that the Bhabha Atomic Research Center was asked to improve some of the signal processing. So were you exposed to that at some stage?
So it turns out that I did not know, at that time I had spent 2 years in 69 and 1970, 69 to 71 at IIT Delhi doing my PhD for 2 years. And I was working on something very abstract, but got enough work to finish up, write up a thesis, but I couldn't submit a thesis. I had done 2 years. So I was back in the Navy, but it turned out that there was a young naval officer who had befriended somebody from Bhabha Atomic Research Center, who had in turn had been to Italy on a research project and was involved with some instrumentation for nuclear physics. And his professor told him that this could be also used in sonar systems. So this young lieutenant, Lieutenant Jane, and he had got together, and they thought they could apply that idea to improve the sonars in the Navy, Indian Navy. So some equipment was put together, and it so happened that in 1971 we had a war with Pakistan, and this particular equipment was on board one of the ships, which is unfortunately sunk by the Pakistani submarine.
Unfortunately, he passed away.
It's at that time when that happened that I was pulled in.
Right. So in 1969, you were nominated to attend the IIT Delhi for the MTech.
Right.
And when Professor Indrasan who, by the way, was also my professor because I went to IIT Delhi. He was very impressed with you and asked the IIT Senate and the Navy headquarters to allow you to transfer to a PhD program. So this was an exception.
Right.
And initially, the Vice Admiral Krishnan said no, but Professor Indrasan persisted, and he was able to. But I think you were allowed to stay there for 2 years initially.
That was the MTech phase. So
Yes.
they said 2 years, and you can do what you want, but 2 years.
Right, right. So you started some work in the filtering theory in your PhD work.
Yeah. So I started initially. Professor Indrasan, who I started working with, was very much a practical person, and he suggested a problem of designing a pulse compression filter for radars. I was looking at it, but I was very theoretical in my inclination. So, and my breakthrough came when Professor Tom Kailath from Stanford came by, and that got me onto a cycle which landed me into a very theoretical subject.
Right. So you were exposed to both the theoretical side from Professor Kailath and the practical side from Professor Indrasan.
They were, I think, they were different influences, but both very powerful.
Right. So in 1971, you left for the Navy's electrical school in Valsura because you had to continue to work on your PhD.
Right. So what happened was in '71, when my 2 years was up at IIT Delhi, and I would have normally, apparently the Navy wanted to send me to INS Valsura, which is a training school in the west coast of India, but that would have taken me away from IIT, and I hadn't submitted my thesis. So I managed, with some lobbying, to stay on in Delhi. So I was then posted to Naval Headquarters, and my hope was that within the next 1 year, I would finish my thesis and then get my PhD, but yet work in the Navy. And in a few months, we had this war with Pakistan, right, which then took me off on a different tangent.
Right. As you were saying that the name of the frigate was INS Kukri. That was sunk through submarine action.
That's correct.
And so apparently Commodore Chatterjee asked you about sonars, and then you went to Bombay with him,
right,
to study feasibility of doing work on sonars.
Right. So what happened was that little prototype that Lieutenant Jain and BARC had put together was on Kukri, which was sunk. So they wanted somebody to look at what was going on there and see whether they could take it over and continue that R&D program. So I was exposed to that when I visited Bach and others. And at that time, I sort of felt that maybe that approach was probably not the most profitable one, but certainly that sonar, which is the British origin sonar, we could do something, we could improve its performance quite significantly. So I wasn't entirely clear about how that should be done, but I said, let me work on it. So I came back, and then I told the Navy, why don't you send me back to IIT Delhi, and I would do that project for you. And it had nothing to do with my thesis, which is very theoretical. And the Navy said, fine. And so I was back in Delhi in December 1971 to work on that sonar project.
Right. But it also helped you to finish.
At least it gave me time to finish up my thesis work.
Right. Very good. So you worked on that, as you said, on the sonar development improvement at IIT Delhi, and Professor Indrasan was also helping you,
yes,
and a team. And then you had a prototype in March 1972 that you flew down to Bombay for a trial on the INS Qatar. And apparently the initial trials had some problems, and then you went back in June after some improvements, and next time the trials went well. And the
That's
production.
correct. It was amazing. In fact, people who could, were amazed that we could improve the performance sonar so dramatically. So it is very clear immediately that this is something that Navy needed very quickly.
And the production was given to BDL Hyderabad.
That's correct. So
after extensive trials in December 1970.
So we handed over the design of the system to BDL, and so they were actually a missile production outfit, but they needed some work, so this was good for them. So they took it on and eventually built a lot of these sonars, which were then outfitted in ships.
Right. So the development of the sonar or the improvement of the sonar, the technology, can you maybe in a very short
way, yeah. So this is a British designed sonar, and it was what's called the Searchlight Concept. The idea there was you had a directional transducer or antenna. You would transmit a pulse and get an echo back to look for submarine. Then you would step and transmit echo. So you would keep walking around all 360 degrees to look for it, to do scanning. And that would take, because acoustically the velocity of sound is so slow in water, that you have to transmit and wait for a few seconds for it to come back. So a full scan would take many minutes. And that was, of course, a restriction. But I didn't really play with that. That was maintained. But what I did was the nature of the waveform we transmitted and nature of the receiver, which involved some very advanced signal processing, was very much improved. And that improved the ability to see submarines, detect submarines, quite substantially. I would think that we probably more than doubled the range of the sonar, and perhaps in some circumstances even more. It was the number of techniques needed to done in it, and many of them were new. I don't think any other sonar in the world had those ideas, but we had some very nice ideas, and lo and behold, it actually worked.
Right. So the difference with the BARC approach versus the IIT approach was really highlighted in this.
So the BARC approach was very simple. The idea was that you send a pulse and you get an echo back, because the echo is competing with a lot of noise and something called reverberations, and sometimes the echo is not visible. So if you repeatedly keep sending pulses, you sort of stay on the direction and do multiple pinging, it's called ping, and you integrate all of them back together, then the chances are that the weak echo would stand out by merely integrating that multiple things. And that was certainly correct. But the problem with that idea was that because it was a searchlight sonar, it had to look all around for the submarine. This waiting on every direction multiple times would slow down that search. So you became very blind to all around you. That was a huge negative factor about that idea. So we decided that will not work. So what we did was actually didn't slow down the searching, but just made some signal processing to make the echoes stand out better. So.
Right. So this was very well recognized throughout, and in fact, because you had improved the British sonar, in 1973, Britain's Loughborough University invited you for a fellowship to work on their submarine sonar project for 18 months. And so that was a good...
Yes, somebody called Professor J.W.R. Griffiths from Loughborough had visited IIT Delhi and saw my work. And so I think he then said, why don't you come over and spend some time with us? And the Navy was reluctant, but finally said, why don't you go ahead? And that was useful. That was a useful trip that I had.
Right. So it was interesting. I read a comment that while you were there, you had fun designing a mini computer. Right. Can you tell me a little bit about that?
So that was 1974. And I think the Intel 8080 or 8008 was available as a bare chip. And so we were using some computers for simulations work we were doing at the university. But I wanted to try and put something together myself. So I managed to find the funds to buy the chip and buy memory, and actually wrote an assembler. And I think I was trying to wrote a little operating system, and was trying to write some basic interpreter too. I don't think I quite finished that, but certainly wrote an assembler. So built a piece of hardware and some software around it. I was very proud of it. It was a way of me learning computing, and it was 1974.
Very good. Of course, then you returned to India in 1975, but before I go forward, obviously your family must have been very proud of you for all the achievements even until then. And I did not read, and I don't know when you got married, for example.
Right.
Feel free to
Right.
tell us about.
So, India, as you well know, those days certainly arranged marriages where everything were happened. So I was, by the time, 26, 27, and I think my wife, my parents were looking around for a bride. And one day they mentioned that they found somebody which seems, generally in India, we look around for a family to marry into, which is of similar social status and potentially similar religion and so on and so forth. So there was somebody available, and so I was flying around India must be on this 170B project. So I flew into Hyderabad for just for one day and met a young woman, and my mother came by and she said, "Are you okay?" I said, "Fine." So a year later, so there was a wedding.
I see. When was this roughly?
The wedding was in 73 February.
73. Okay. Okay.
And
so
then I just was finishing up the sonar project.
I see.
Submitted my thesis, which my wife actually helped me edit.
Oh, okay.
It was full of so much. It was full of measure theory and lots of formulas, and typing it was a big effort. And so my wife helped me with that, and so I submitted my thesis, got my degree, got the product manufacturing launched, and then went to England.
Okay. Did she go with you, or?
Big one. She came with me, yes.
Okay. So you returned to India in 1975, and then you installed the mod kit, as it's called, which you developed in England, apparently. Is that true? Or the modification kit?
Yes. This was the 170 project.
Right.
It was called mod kit because we've done it at IIT Delhi, because we only modified the receiver and the transmitter. We didn't change some of the other parts of the sonar.
Okay.
So it's called a mod kit, and this was the one project I'd worked on. And by the time BDL had manufactured these units, so I was involved with their deployment, their installation and deployment.
But I read somewhere that while you were in England, you also had done the mod kit in England.
No, nothing in England.
I see.
So what happened in England, which sort of, this was the project at IIT Delhi was a nice project, but I didn't really see myself as a future in sonars. But when I was, and I did not know this, but the Indian Navy, because we lost the ship, was now looking for a really top sonar, what's called a panoramic sonar. That is something, because those searchlight sonars are very disabled by the searching process. You want to look all around simultaneously,
right,
like a 360-degree phase-digit radar. And those sonars were available in the US and from Russia. And we were looking for the top-of-the-line sonar, and apparently we were looking for that, and the Navy had caught us. I wasn't aware of it. But they did tell me, in the Navy did tell me, said, we have given some orders to French and the American and the British to build these advanced sonars for us. Why don't you go and have a look at this project? When I was in England, I went by and visited them, who were working on sonars for the Indian Navy.
I see.
These are more advanced systems. And I sort of felt that maybe we can do it in India too. So when I went back to India, I became aware that Navy was looking for a more advanced sonar. So I lobbied them, saying, why don't we let me do it? So then I was moved to a lab in Cochin,
right,
and headed the program.
The National Physical and Oceanography Lab, NPOL. So before you went there, you installed the mod kit and the INS Talwar.
Yes, I think it went in many ships, but I might have been installed in one or two. I might have done that.
Okay. So you moved to Cochin, then with NPOL, to work on the panoramic sonar. And in 1976, work started on the Advanced Panoramic Sonar Hull-Mounted APSOH.
Yes, absolutely.
And I think when you moved to, there was an interesting episode when you moved to Cochin. I read that initially there was not a lot of excitement about involving you because work was already going on. And then there was a computer that arrived damaged, and you fixed it, and Mr. Srinivasan really was impressed with that and got you into the...
I had a PhD and I'd done a sonar project, but I was in uniform, and in the labs we didn't really look at uniform people as somebody who would build anything.
Right.
So I think initially they were didn't know exactly what to do with me, But then it was a PTP-16 or PTP-11 computer, which had taken some banging and was some problems, issues with it. And I managed to get it to work, and so that finally got me involved in the project. So then I sort of took it to higher speed and built and then built a team to do it.
Right. So in 1976, work was really started on the APSOH, and the C trials were done in 1979.
They were, I would say, of early prototypes. So I would say bits and pieces. Because we were building, it was an active passive sonar. It had lots of different pieces to it.
Right.
So those pieces would go out for trials in 79, 80. But the full-scale system, which was a fully engineered, almost production-worthy sonar, was finally tried for almost for many, many months, because we had to yank out, that required taking out the old sonar and putting the new one in.
Right.
I think INS Himgary was the ship that we chose. It had an existing sonar, a British origin sonar, so that was yanked out. And these were big animals. They would occupy multiple compartments. So it took 6 months to take out that sonar, put the new one in that was developed by my group. And it was, the system was actually manufactured by Bharat Electronics in Bangalore.
Yes. So the
So
circuit
it almost
design,
took us 6 or 7 months to install the whole thing. And then we went out to sea in 1983, I think, first time,
Right.
or maybe in 82, end of 82.
Right.
And it was a dramatic success. It was unbelievably performed so and well that it's certainly better than any sonar that Indian Navy has seen from anywhere in the world. So it was clearly a winner.
Right. And I think you also played a key role. There were a lot of issues between NPOL and Bharat Electronics.
Right. There was always the finger pointing because we were kind of the design agency and they were the manufacturing agency. And those days we were living in they had to build printed circuit boards. We were using MSIs, LSIs, but we would send these circuit diagrams to them, and we would make mistakes in those diagrams, and they would build the wrong board, and so those things went on. There was lots of time pressure, but I think once we got to see and things began to work, I think it settled down. There were, of course, some hard times in between.
Right. So in retrospect, I read you said that I'm always amazed as to how such an inexperienced team with such few resources pulled off this major project in such a short period. APSOH was an impossible dream that came true for many of us. These are your words.
I would still agree. And in fact, doing this project, which took many years, I would run into Raytheon and into the Alcatel, people who would traditionally build these large systems, and the Russians too. And they would say, Paul, this is impossible. This is just, you don't have the wherewithals to build such large systems. And it's not easy to do. And the team was very minimal team. And I think I was a PhD and some mathematics background. We had probably somebody else from computer science background. But and we certainly had an engineering team in Bharat Electronics who knew how to build a product. The design had to come from us. So it did seem thin on the ground, but somehow everything worked out.
So in May 1983, as the APSOH trials were concluding, Dr. Arunachalam, the scientific advisor to the defense minister, you were, of course, had a very prominent visible role in the Navy, asked you to leave the country on a sabbatical for 2 to 3 years to do something different. And so after 11 years of cookeries, sinking, your sonar career sort of came to an end.
Actually, it was interesting that, in fact, the idea was to take a sabbatical and do something.
Right.
And partly to sort of break from the high-pressure project. And then I landed up at Stanford. And then Arunachalam came visiting at Stanford. He was probably shopping around in the valley those days. And I remember in a dinner, maybe it was with Lockheed Martin, and Lockheed Martin CEO was there, and he says, Paul's sonar career is over. He's going to do something else now. That's the time I heard. The Indian government said, no more sonars.
I see. Okay. So in September 1983, I think you contacted Professor Kala.
I wrote to Tom when Arunachal said, why didn't you go? I wanted to go back to England, to Loughborough, and you sort of knew about it.
I see.
But he said, no, you go try and think, why don't you think of Stanford? Do you know anybody there? I said, I do know Tom Kala vaguely, and who was involved in my PhD thesis. He said, write to him, tell him that you have a scholarship from Stanford, from government, Indian government, why don't you go there? So I wrote to Tom.
Okay. So you talked to Tom, and he eventually asked you to join Stanford as a visiting faculty.
Right.
In 1983.
1983. Actually, initially he said no. He wrote back saying that, you're a kind of a real engineer, been building systems, and we are very theoretical here. I'm not sure you would fit in anymore because my work, he knew about my theoretical work earlier, but I think my second letter or third letter, so I think he changed his mind.
Okay. So you came to Stanford, and your initial work was purely theoretical, mostly in applied mathematics, is what we read.
I actually landed in Stanford, and I had never looked at the whole area of mathematics called linear algebra, so never crossed my mind, because my thesis was always was very much in stochastic calculus and measure theory, and this was a big tool which I'd never seen. So, but this is the tool that was extant in Tom's group, and they were looking at some direction of arrival estimation problem.
Right. When I was doing Tom's interview, I realized that when I read about the work on multiple signal directions of arrival, that I think some of that work started at MIT under Shannon, and Professor Kallat's thesis involved that. He was given that as a task.
I think he was looking at multi-part propagation issues, modeling, and I think there was some overlap with those ideas and this idea.
Right. So you worked on a multiple signal direction of arrival DOA estimation problem that had a long history of improvements using a spectrum approach. Then you proposed a totally new method called Esprit, estimation of signal parameters via rotational invariance techniques, which caused a mini revolution. So maybe you could talk a little bit about that.
And that was a very interesting way I came about it. And it goes back to my APSO sonar days. It turns out in APSO sonar, it had many features to it. One of it was finding the direction of arrival of passive, that is radiated noise by submarines. You can localize them. And it turned out the right way to do that would be to take a beam and scan a beam and look for the maximum of the beam response, and that would be the direction of arrival. But there was an alternative method which I was playing around with, and that was you can take two half beams and add them with a negative sign. Then you would create a beam where you got a dip in the center, a sharp null in the center. And you scan that, and you look for a sharp dip in the energy, and that's the direction of arrival. So you're scanning a null, not scanning a beam. And a null superficially looks better because you get a very sharp null. So that might give a better accuracy. But it turned out mathematics showed that you had to scan the beam, which intuitively seemed to be the poorer method, but that was actually the best method. So we went back to the best method. But this idea of this null steering was in my mind. And but with multiple signals coming in, null steering does not work, because when you start steering, one signal may disappear if it's in the null, but the other signals are coming in, so you don't get the dip in the energy. So I was looking for some other mathematical object which would go to zero when you sort of one of them was removed, and that led to the Esprit algorithm. And that became called subspace fitting, subspace methods, rotation methods. And so Esprit launched a whole paradigm of thinking, which is pretty important today.
Right. And apparently many papers was published. I read like
well over 1,000 papers have come through, many applications.
50 doctoral dissertations.
Right. I think even right now, I understand it's being used in biology, and it's got many applications now.
So the applications go far beyond the array signal processing to spectral estimation and to system identification.
And of course, I remember once this Professor Wozencraft, who was a very well-known professor at MIT, very famous book, Wozencraft and Jacobs' book on communication theory. So Wozencraft came visiting Stanford, and I was telling him about Esprit. He said, "This is the best thing I heard since that's to bread and butter," because it is such a neat idea. And it was anybody looked at it would say this, and they would always say, "Paul, where did this idea come from?" It's so different.
Right.
Because there was a long history of this problem that all took a different approach.
Right.
And mine was a completely different approach.
Right, right. So it's the physical rather than the mathematical insight.
It came from physical insights of I think from sonar days, which led to the mathematics.
Right. Generalization of the sonar work, as you mentioned. Then, of course, since you were on visiting role, you returned to India in 1986 and served as the founding director of 3 major labs. The Center for Artificial Intelligence and Robotics, Center for Development of Advanced Computing, and Central Research Labs of Bharat Electronics. So how did that come about?
Happened, yes. So, so when I went back in 86, I was, obviously, so they wanted me to take over a very large lab in electronic warfare, which India had, a defense lab. But that had about 4,000 scientists, and I was pretty young. I was late 30s, I think, at that time. The people said, this is not something that you'd be able to manage. You'll be just pushing papers. You're still young and you can do some science. So do something. If you want to do a lab, do something new. So that led me, and the defense was not keen about it. Different DRDO. But then I spoke to the naval chief, and naval chief told the defense that let Paul do something new. So I knew nothing about AI, but I said it seems a nice idea. I started the AI lab for defense and robotics. And I ran into Professor Raj Reddy, who came by several times. So we knew that that was still a very infant technology, and any real products for the defense may take many years. So I said, let's build some foundations in the lab. And at that time, expert systems were the big paradigm, expert systems. So I was looking at those items, building a small team. But then at that time, we had a major program for a fighter jet program in India called the Light Combat Aircraft Program, LCA. And that, I think the government felt that it needed a leadership, and they thought that I should lead it, because I had done a big sonar before. And at that time, I was probably the first person with such a large success story behind him. So I was co-opted to run the combat jet program. So I did a certain amount of flying and getting to know things, and so I was still not enter the program. I was trying to build a feeling for combat jets, visiting, did a lot of traveling and so on and so forth. But then when I was getting closer to the program, I requested a structural change how the program is run. I won't go into the details, and I was very heavily involved with the Air Force, met with the Air Chief many times. And the government, Dr. Arunachal said, no, we'll get it done, whatever you want. I actually wanted to do it as a private-public partnership. There were some details I want to go into it, because I found that the government at that time was very constrained in the way things worked. I mean, ridiculous constraints. I said, and I remember Dr. Arunachal coming to me saying, I want to fly the aircraft in 1 year, and you better get moving. So I said, let's take it out of the government partially. So it turned out that didn't work out, and finally the Navy said, didn't think I was going anywhere with trying to reconstruct the program, so they took me back into the Navy and assigned me to Bharat Electronics as a chief scientist to build some technology because Bell was the core company, the company for military electronics in India, and they supplied all the armed forces with communications, radars, sonars, and so on. So they were actually also manufacturing the APSO sonar. They said, why don't you build a more fundamental lab so they can be better able to build systems? So that's how I landed up in Bell and started that lab for them. In meanwhile, there was somebody called Mr. Petroda,
yes,
Sam Petroda,
I met him,
who had heard of me, and he was trying to put a high-speed computing lab together called CDAC. This also was sort of linked to the United States, because we were trying to buy, I think India was trying to buy the Cray from here, from the United States. And US was willing to sell it, but they didn't want us to use it in a nuclear program. So they said they wanted some oversight of its use, which the Indian government said, no, that they can't accept. And Mr. Pitroda, in his usual, said, I will build it for you. What do I do and import it? So Pitroda asked me, said, why don't you try and get involved with this project? So I was sort of doing the computing project and the lab for Bell simultaneously. But then I told Ms. Pitroda that building a Cray, we don't have the semiconductor ability in the country, because those require custom chips.
Right.
It was too long a bridge to
In
cross.
fact, I was going to ask you, so at Bharat Electronics, they had a manufacturing plant for semiconductors?
We had a small plant, and I think it was, many microns. It was already at that time way behind the world standards, and that was certainly not anything that could do. I think it was doing very small chips, watt chips, and nothing like a Cray.
Right.
So so we said no, we're not going to do Cray, but we have to rely on imported semiconductors. So the only thing we could do was parallel computing, massive parallel SIMD machines. So I took the lab project towards message passing parallel machines, which we knew, thanks to Amdahl's law, would not scale well in many problems, but some problems it will do a pretty good job. So that's how I got involved with that lab.
Okay. Thank you. So as you mentioned, what made you come back to Stanford?
Okay. So that's a big question. But I think my experience with the light combat aircraft program was not very good, in the sense that I could really see that this is a very important national project, and I'm not sure I would have succeeded, but I had a good chance of succeeding because I had done something before, and I certainly had a reputation for getting things done. But I did find that there were lots of bottlenecks thrown. Some of them were part of how things work in our country, but some things were probably aimed at me a little bit. So I just felt that then I joined Bell, and I realized in Bell too, I was certainly there because the Navy wanted me there to build Bell up, because Bell was the supplier of lots of the equipment. But Bell itself didn't show very much interest in any kind of a research lab, fundamental technologies. I mean, certainly we were not a research like Bell Labs. This is fundamentally to build early prototypes of encryption machines or radars, sort of to help the main manufacturing plant get onto that technology. And but clearly I wasn't making much. They weren't very convinced that these things were important. And Bell unfortunately was very much prone to importing technologies and building them on license. So it seemed a bit of a misfit. So then I just thought that if I want to do, and second, I always was very interested in mathematics and mathematical thinking. And I really enjoyed my stay in Stanford. I said I want to go back to academia and do research and get out of this building products. And an obvious thing was to go and join an IIT. But I did check around a little bit, and many IITs would have told me, I don't think I approached them formally, but they said, no, you're a naval officer with an Indian PhD. Those two things don't make sense for an IIT. We want a foreign PhD, and so nobody from the armed forces. So I just thought that IITs would not somebody they would hire me. And so I wrote to Tom, and Tom said, things not looking good here, we were going through recession. But why don't you come along, join as a postdoc, and I'm sure something will figure out for you. And your work in Esprit is well remembered, and that's how I came back. It's not clear what I will do. Right. I said, let me come back to Stanford and figure something out.
So Professor Indrasen would have been one choice to approach.
That's true. And in fact, Professor Indrasen by that time had retired.
I see.
Had retired. Okay. Was much less active, and it's facetious for me to say that IIT would not have hired me. Certainly, Indrasen would have talked in my favor, but also I would say that even that time much of my career was always in labs, and the IITs were very much into paper writing papers, and I'd written certainly a lot of papers at Stanford, but I was not. I think I sort of realized that I came from a builder culture, and probably not somebody would be interested in writing too many papers.
Right.
So and clearly I think the fact that I had an option at Stanford certainly overrid any options I looked at seriously in India.
Right. I remember Professor Andreessen came here and we had lunch together with our group. And I remember his card had a government designation, like he was working for the government.
Yes.
So he had a role, like advising.
Yes. No, I think he was probably could have been the president of the Indian National Academy of Engineering. He was the president of that.
Could have been that.
Yeah, I think that might have been the one that.
I see. Because I know he had already retired.
He had retired. Yes. In fact, I did actually try through Bell to get some fellowships for him. Those days, you retired at the age of 60, and you just went home. And somebody of his talent, it was a shame. So I think I managed to get him some professorships for a few more years at IIT Delhi through my influence.
I see. So when you came to Stanford in 1991, while awaiting a faculty position, you worked on a signal separation experiment for airborne reconnaissance. So was this for the Air Force?
Yes, this was, so when I came by, obviously somebody had to pay my salary. So I think Tom had some money to sort of get me started, but he was always trying to find somebody who would pick up my salary. And of course, I think there was enough noise in the department saying that they should try and get me inducted as a research professor. And so that process was starting. But that was it's clearly a one-year process because you got a lot of letters and things like that. So there was somebody, well-known professor called Professor Gene Golub, mathematician, who had a DARPA program to look at this airborne reconnaissance problem. And it had a long history of mathematical algorithms, and apparently some of them had some instability in them. They would break apart. So he was asked to look at how to stabilize the algorithm there. So Gene had known me from earlier visit. So he welcomed my help. So I was working with him and got my salary too. And then, those days everything was done in MATLAB, you had this thing. So I said, why, when you do math, you live in the MATLAB world, everything you create is MATLAB and it may not be the real world. So let's build a little prototype to sort of simulate what the problem was that we're trying to solve. So I had, I had enough skills to put something together. I'd used cordless phones as a source of signals, and we was playing around with it. And I think it's like kind of a wax instinct prototype, touch and go. And while we were doing these experiments, we would find that those phones were far apart. Things would work as expected, and when the phones went close, the system will not work because the underlying matrices would blow up. Exactly what you expect. Right. But one day it rained, and we pulled that antenna structure into the foyer of the Durand building. And I think I had requested some student colleagues to help me with this, and I think they sort of had come by to each other, and we could still see that they were next to each other, and the system was still separating them. That was completely unexpected. That very quickly, over a matter of half an hour, it clarified why that happened. It happened due to multipath. The presence of multipath made that possible. But immediately I said, this is interesting, but it was relevant to the Air Force project because that problem didn't work out in Air Force project. So I sort of dismissed the idea, but apart from the fact that I had sort of discovered this neat angle to it.
Yes.
But some days later.
In fact, you were sitting in a barber shop. Yeah.
I was sitting in a barber shop in Mountain View, and I was saying that, these two phones could send signals from next to each other, and you could separate them. What happens if you have two antennas on the same phone, and you have two streams coming out from the same channel? If you can separate them, then maybe you might be able to increase the capacity. So I went back and did some quick calculations and said, lo and behold, if you have M antennas on each side, you can get M times the capacity with completely fair. There was no extra power involved, and so it was a clear win. And so that was a sort of great idea. But then I was troubled by a very important problem that I noticed. So when I noticed that you could separate them from next to each other, so if somebody moved a couple of inches or somebody walked by, it would fail. It was, now you see it, now you don't. Now you see it, now you don't. And I was saying, how can this be applied in phones? Because it's not a reliable way of getting capacity. So I was trying to engineer the problem to a way it would be reliable. And so I said, in broadcast problems, if you put this on rooftop, things might work better. So I was trying to find a paradigm where it will really work all the time. And then we wrote a patent, and the patent, I emphasized that application first, but I did say it can be applied in mobile communications too. But what missed my mind, and of course, I should have noticed it, is that that's how it works today, except that we keep on toggling. We say it works, we use it, we don't work, we don't use it. And that's how your phone works today. That seemed to me improbable at that time.
Right. So that the patent you mentioned was the DTDR.
That's right.
Distributed transmit.
So that was
directional
taking the idea of MIMO and sort of engineering it to make it work in a way it was guaranteed to work all the time.
Right.
And it turns out that is now being used in television broadcasts too. But the first applications came in mobile, where it had to use this now you see, now you don't way it worked, and that's how things work.
Right. So the patent was granted in
1994.
September 94. And it now is known as spatial multiplexing.
It's called spatial multiplexing.
And it boosts the spectral efficiency by creating parallel spatial data streams within the same frequency channel.
Right.
Again, it was the visual thinking, just like it started from that spark.
That's correct. It was visual thinking, and it was also physical experiments. So from the physical world, the idea came. It wasn't something that's sitting in front of a whiteboard and thinking about it. So
right. So it's very interesting that Esprit and then MIMO.
Both came from the physical world.
Yeah. You were appointed a professor of research in '93, and you built a large research group around MIMO, and you graduated more than 50 docs and postdocs. The spatial multiplexing techniques make the receivers very complex, and therefore they are typically combined with orthogonal frequency division multiplexing, or OFDM. Is that, can you
I would put it this way, that is, so the MIMO was a concept which could be applied across, in a wireless system, there are two aspects to a wireless. One is the modulation, how do you modulate the signals, and there are different modulation schemes.
Right.
Then there is also a multiple access scheme, where how do multiple people access the base station. And there was, so far, if you look at Gen 1, there was this, it was FM modulation and FDMA, that is, everybody had a separate channel.
Right.
And in the second generation, it was TDMA, where everybody, we still used a modulation called, digital modulation called QPSK, but the access was done on a time slot method, time division multiple access. And third generation used CDMA. And the modulation was spread spectrum modulation. So MIMO could work on top of all of them, but I think it turned out that there was one particular modulation called OFDM, where it worked the best. Not so much, certainly partly from the computational point of view, but from actual performance. You could do a better performance, much more cleaner performance with OFDM. And OFDM has a multiple access component called OFDMA. So MIMO OFDMA was the right combination, and that coming together didn't happen at Stanford so much as when it started Iospan. And so there it became clear to me that this combination was the right combination, and at that time the dead center of all wireless world was in CDMA.
Right.
And you mentioned not CDMA, everybody said no, we don't believe in you. Right. So it took some effort to, and certainly Qualcomm for a long time didn't think it would be a good idea, because they were embedded in CDMA.
Yes, I understand that there was a very strong skepticism.
Very strong skepticism. In fact, I more than once met with their leadership, and they point out every reason why it will never work.
Right. And especially the practical feasibility. From a concept it was okay, right, but as a practical solution.
And in fact, it turns out in CDMA, CDMA has some nice advantages to it. And for, I think, voice, it was a good system. And it had some advantage called interference diversity, which is a very positive advantage. With MIMO FDMA, it turned out that you couldn't do as good a job as you could do with that in CDMA, that particular aspect of it. So we had to invent a few things at Iospan to sort of try and get there. But so CDMA had some advantage in one angle, which OFDMA never fully got into. But the fact that MIMO worked well with it was a big advantage. So MIMO FDMA has now become the gold standard of all wireless. Right. Wi-Fi uses it, 4G uses it, 5G uses it. Right. It seemed to be used forever in the future. Right. We never know.
And it's got the scalability.
Beg your pardon?
Scalability.
Yes, for example, yes. You can keep on increasing antennas. You get to see, the throughput keeps on going up, and increasing the bandwidth and increasing number of tones in OFDM. So it scales very well too.
So let's go back to Iospan. So you founded Iospan, and that became very successful. And then later on, you sold it to Intel in 2003, and that basically made the MIMO feasibility, that proved the feasibility of it.
Right. I would say yes. So when in Iospan, the focus was a cellular system like we have today, but not a fully mobile system with handovers, because we just felt, I think correctly, a mobile system needed a global standard to be in place, because it's a large, vast ecosystem. People had to build phones for it and all that. So it needed to be standardized, and we as a startup company, standards was not possible. So we built a fixed cellular system, but for fixed access and nomadic access, like a laptop, you can go anywhere, and like a Wi-Fi access. So it wasn't standards based, so we were building it, and we had lots of demonstrations around the Bay Area. We actually had kind of a customer of all places in Dubai. Somebody was looking at it. We were doing some customer trials. But it's clear that by that time, by 2002, the future of this was in mobile systems. And clearly, we could not do it. And so Intel was convinced at that time that mobile internet was the future. So they were looking for a technology which would take them there. And they saw this was a good idea. So they picked the company up, and then they sort of dubbed it WiMAX. And so I remained with them for a few months, maybe for a year as an advisor, and they began to build chipsets for it and began to drive the standard, the WiMAX standard.
So going back a little bit, how did your family fare? Because you were going back and forth between countries.
Right. I think it was good on one side. I mean, they saw my children, for example, were India, then kindergarten here, then went back to middle school India, back to high school here, and one of my girls went back to college, back to India. So there was up and downs. I think it's a little tough on them because India has a lot of languages to learn and those sort of things, and so there was some disruption of that. But I think the enrichment was also there of different cultures. So looking back to them, I think they would not consider a negative. You must remember that most of the shuttling, I was still in the Navy, so I still had this one job, till I finally came to Stanford in 1991. I was always at the same employer, so it wasn't disruption of a job, and so that safety factor was there.
There was always a continuity.
A continuity, yeah.
Right. And then in 2004, you co-founded BSIM Communication. So this is more in the semiconductor domain.
Right. So I was just finished up with Iospan, and I was back at Stanford, and it turned out that I had used up all my leave, and I didn't have any leave left, and I thought I'll write a book on MIMO. So I was busy writing the first book on MIMO was written by me as a textbook. So I was busy doing that, and so one day somebody showed up in my office saying, "Can I meet with you?" And he said, "I've been doing semiconductors for DSL, and I want to move to wireless, and can you join me?" And I was initially very hesitant for some time. I kept saying no, saying that I want to finish the book and things like that. But finally, one of the venture capitalists who knew them took me for dinner and said, Paul, no, the money is available for you, why don't you join? And so that got me into BCM.
I see. So the semiconductor part, I guess they provided the technology, or the other person?
Yes, so I sort of brought all the wireless piece into it. So I brought my students joined. So we brought, certainly at that time, MIMO, FTMA had been established. But so the semiconductor piece of designing chips and the front end, back end, all that they brought. Okay. But the systems piece I brought. Okay. So it was a good combination of both. Right. And it was a very successful company.
Right. And at one time, you had 65% of the market.
Yes,
share.
we were clearly the leader, 65% of the world market. And BCM was not a big market, but we had reached about $100 million revenue, and that was 65% of the market. But I think at that time, it's interesting that later on I discovered this is true, that WiMAX had a chance of being the 4G standard. But it somehow tread on some political issues around the world, and so the Chinese were against it. I think they thought it threatened their own system called TD-SCDMA, and so 3GPP people who were at that time doing the wideband CDMA, the 3G CDMA, they saw WiMAX rising, and they said, we can't keep rejecting MIMO FTMA. This is going to happen. Right. So they jumped onto it and created the standard called LTE. Right. And so that's basically WiMAX rebranded as LTE.
Right, right.
And then because that time it was LTE was aligned with everything in mobile cellular, that became the dominant thread. WiMAX, because it came from the IEEE side, didn't have that advantage. So finally, WiMAX is sort of still there, but it's not quite there. So LTE became dominant. So in BCM also, towards the end, we began shifting to building LTE chipsets. Very similar technology.
So the 3GPP standards group was the one that...
Yes. So 3GPP standards group was formed around to promote the standards around CDMA standard, 3G standards. So they haven't changed the name. They actually took on OFTMA and called it LTE, long-term evolution. They didn't change the name, though it's called 4G. And now they're driving 5G now.
Right. So with all your achievements, your Stanford colleague and Marconi Fellow Professor John Chaffee, inventor of the DSL technology, calls your technical capability almost unparalleled in the world. What impressed him most is how you endured the tremendous pressure, turmoil, and stress of people saying, your ideas weren't going to work, and you persevered until you found success. People such as you are pretty rare. This is coming from an esteemed colleague and a peer, so it's a very high praise indeed. You have won the two top telecom recognitions, the IEEE Alexander Graham Bell Medal, which emphasizes theoretical contribution, and the Marconi Prize, breakthrough ideas that products benefiting billions of people. So again, this is really amazing. So you have also mentored many people at Stanford. Can you say a few words about your
Right. So
of course, you were honored with your book on MIMO on your 60th birthday,
right.
with a preface by Professor Kalat.
Right, right. Well, I think the great pleasure at being at Stanford was working with students, and Stanford attracts very good students from around the world, and so I had a whole bunch of students from pretty much all across the globe, and it's a relationship with students is lifelong. They're due for the PhD time, but we sort of remain with them for all the time. So it was, and then not only students, but also postdoctoral students too. They stay shorter periods, like a year or two. So I maintain, I think, very active I wouldn't say collaboration, but certainly relationship with almost all my students. And you're always there for their promotions and for their awards and helping their career. And when I travel, like I'm going to travel to Europe next month, on Monday, you run into their students everywhere. So it's been a larger family for me. And so I think truly, I would put that, the student relationship as the best I had at Stanford. And occasionally, Stanford, sometime what I do is I would pick up a student from some other group who's sort of falling apart and having some difficulty in finishing up, and take them on, and like the story from My Fair Lady, you sort of make them into a star. I've done that a few times too. Sort of spend time with them and get their self-confidence back, and get them, because in Stanford there's you go through a barrier called the oral exam, and very often that turns out to be, if student has not been coping with it, that becomes a barrier to go through. And so I would sometimes meet them almost every second day for a few months to get them through, and I've done that a few times.
Very nice. So let's talk a little bit about the future.
Right. Also, we should talk about India and my involvement in India at some time.
Yes. So the potential for MIMO to multiply capacity in wireless spectrum seems as limitless. I think you mentioned millimeter band frequencies can soon enable a much larger number of MIMO antennas and corresponding boost in wireless capacity. Can you spend a little bit of time on that?
So in the way MIMO works is that the number of antennas, there are versions of MIMO, I won't go into that, but fact is that you have a lot of antennas, you can do more with MIMO. Every antenna sort of gives you one more reuse of the same channel. It gives you an additional channel reuse for every antenna. So at millimetric band, in the current LTE, for example, that we see around, we use, they sometimes use frequencies as low as 700 megahertz. And those antennas at the base stations are 6 or 7 feet high and about 8 inches wide, huge antennas. You can't put many of them in a base station. But at millimetric band, like 29 gigahertz, or 28 gigahertz or 39 gigahertz, the antennas become really small. It's just a few millimeters. So in a small panel of 6 inches by 6 inches, you can have a few hundred antennas. So obviously at millimetric band, the amount of antennas goes up dramatically, and therefore the leverage of MIMO increases enormously. And also in millimetric band, there's a lot of spectrum available. Spectrum is very scarce in the lower bands because everybody wants to use it. And millimetric band, the spectrum is easier to is more available, clearly because almost all of us today in mobile communications are crowded at 2.5 gigahertz and below. But millimeter band opens it up all the way to 100 gigahertz and even beyond. So obviously lots of spectrum there. So the high bandwidth and the high MIMO leverage together combines to give you a factor of 1,000 in the future of throughput, 1,000 times. And with the future of wireless called 5G, where we're going to go into IoT and many other applications, we will need this bandwidth. So I think there's a demand for it. So to come back to MIMO, the millimetric band enables a lot of antennas. But there are some challenges. One challenge is that the millimetric band, it actually, except for a particular band called 60 gigahertz, where you get some absorption of radio energy, the transmission of energy at lower bands at 1 gigahertz or at 30 gigahertz is the same. Photons actually fly the same way. But you don't get much range from them, because when you have an antenna at say 1 gigahertz, is a big antenna. You pick up a lot of photons. But when you get the antenna so small, the photon flux is the same, but you don't pick them up so much. So you get a lot of reduced range. So the one way to build range is to put a lot of antennas and then form a beam. And so beamforming, millimetric band, MIMO all come together in a very nice way. So today, there's huge push of 5G is massive, we call it massive MIMO, because MIMO in a huge scale. And it turns out, interestingly, a lot of problems of signal processing, which are very important in the current technology. 4G, we spend a lot of energy trying to implement the receiver. It's very complex to implement. But in 5G, in millimetric band, we have a lot of antennas, things become easier, which is, rarely does nature give you that gift, but it becomes easier. So that's a nice thing. But it turns out that there are other hardware problems. For example, if you, today in each, in a LTE base station, behind each antenna, you put a ATD converter or D2A converter, and then take the signal back into chips to do the processing. In millimetric band, of course, the bandwidths are much higher, and typically, let's say 1 gigahertz. So if you want a 1 gigahertz AD converter sampling rate, it turns with 12 bits of AD conversion, it's about 4 watts of energy. So 4 watts of energy for the AD conversion, so 4 watts for D2A conversion, 8 watts per antenna. We have 64 of them, 128 of them. It's not easy to do. So there are a lot of new challenges of trying to build circuits for massive MIMO which are feasible in terms of power and so on and so forth. So there's a lot of research going on to solve these problems. But the way it will first come in millimetric band is we will actually just use antenna panels with a lot of antennas just doing beamforming, where you can do the beamforming in analog means, so it's not using AD converters, only one AD converter per panel, and then do MIMO across the panels. So the MIMO leverage may be small initially, you may still have a lot of antennas for getting the link range going, but slowly you'll find that the MIMO leverage will go into each antenna. And at that time, we will get this huge boost in capacity, but I think we got to solve a lot of other problems in between. So I would say full-scale MU MIMO, massive MIMO may take a few more years, a lot of issues to be solved, a lot of interesting theoretical problems also. But a simpler version where you're using millimetric band and low order MIMO will happen very quickly. So there's a lot of work going on around the world now, literally thousands of researchers and engineers looking at these problems.
Does the noise in the world becomes an issue? Noise of the signals become an issue at all?
I would say not necessarily, no. It just turns out that if you have a very wide channel, you pick up more noise. So to that extent, your signal is competing against more noise. That comes from channel bandwidth. And that's something we live with all the time. Yeah. So there's nothing specific about millimetric band that makes it worse. Okay. So massive MIMO, and MIMO will certainly expand its value enormously in 5G. And I think the massive MIMO angle will take a few more years because there are a lot of hardware problems to be sorted out. But it'll come, and it will finally deliver what we think is a 1000x over today, or 1000x factor.
Thank you. That was very nice. Thank you. I have only mentioned a few awards and recognitions. Of course, you have had so many more awards, and you're a member of so many academies and so on. So sorry that I didn't. I think a lot of it is visible on your website, and so I will not repeat it.
No.
But I really want to acknowledge that you're very well recognized and deservedly so. You and your wife have been frequent visitors to India to emphasize the need for India, for example, to build its own telecom technology industry. What are your thoughts about
India?
India?
Yeah, so because I've worked many years in India and obviously I've not lost the connection, I've always felt and I've observed that India has done well in some areas of technology, like the space program. So we have a space program. We have launch vehicles and we have satellites.
There's been some amazing results.
Right. And some of them we've done with very low cost, yes. Mass probe. So we have these islands of technology. Space is one of them. And I would say within the defense R&D, we had certainly an achievement in sonars many years ago, more than 30 years ago, which I led. But after that, there have been other programs which have done well too. And so there have been some islands of where India has done well in technology. But in mass market, that is where hundreds of millions of people use the technology, whether it's laptops or cell phones or it's in televisions, those things we tend to import en masse because those are highly competitive, and these are global ecosystems, and we've not been able to build companies to compete in that world. And of course, I've been seeing the rise of China. China has done very well in some of those areas. So I've often asked this question, saying that India should get into that because is that because today the import bill is pretty large. I think in around ICT, our import bill is probably $150 billion. The number, give or take a few percent. And it's growing, and with 5G, where it's sort of 5G will underpin all the things in smart cities. There's a lot more applications coming in. The import will be much larger. While the programs that we've done well, like in space or in defense, those are, if you look at the value addition to the country, those are very small, sub-$1 billion. So I will be saying, why can't we try and replicate that strength in the mass market technologies? They're not easy because then you got to take on the Qualcomms of the world, the Intels of the world. They're not easy to do. Or even when it comes to box companies like Cisco and Huawei. And but nevertheless, India, I think, is very capable of building companies there. So I've been, for many years, looking at this, and I've been involved with the government in various ways. And when I can compare China with India, I know China reasonably well. So China, the government is a very active player in technology policy and writes big checks and takes big bets, and not all of it succeeds, but some of them do. India, as structurally, we are organized a different way, and I think those things have not happened. Where it's completely government-owned for defense of space, things have worked. But in civilian technologies, I think the standard traditional traditional way of doing it is through private companies, and government doesn't fund them. So I've been trying to find various ways of doing it, and been involved with the government in trying to create funding for startups through the government, and there are different models in Hong Kong and Singapore, and written some white papers and been on some committees with them. But we've not moved the needle very much so far. I think maybe things are improving. So recently, for the last few years, I've been sort of focusing on working with IITs and getting them to build prototypes, so get their hands wet. And with that, we have very, very young, very, very smart young professors. So get more self-confidence in building things. So hopefully, they could then be from bootstrap into building companies. We have very good researchers in India who write good papers, and if you go to any international conference, you'll find Indian researchers show up. But the complementarity of building tech companies has not happened as yet. Of course, we have a very successful IT services company and an engineering services company. So all of us, work with them. You work with them in India. I do too. But we need to go to a point where we hold IP and build innovative companies. So that's been a big factor, and I've been going back to India many, many, many times over the years. My wife, of course, has family links there. So we're there very, very often. So I think we will get there eventually, and there is no question India will get there. It's a matter of trying a little bit more. Mm-hmm.
Thank you. So some comments about your advice to the next generation.
Right.
With all your experiences and as an academic and also working in
right.
the field, what would you recommend?
Right. So one thing, I'll just talk a little bit about my own professional background. I think I've benefited particularly from mixing theory and practice together. It wasn't that organic. I was fundamentally a practitioner for many years in India. That was my job, building systems. And coming to Stanford, you went back and you got into theory. So I've been able to walk in and walk out of these two corridors fairly well, rooms very well. And I found that very enriching. I think, in fact, I would say almost whatever ideas I have in theory, which I'm sort of recognized for, often come from the practical world, and we discussed that earlier. And certainly when you build systems, whether it's wireless or even sonars, you really want to have your theory straight to make sure that works too. So it's been that combination has been, I think, very good. In my background, has worked well for me, and I think I was just lucky. Many people who joined the university early in their lives would never get this opportunity I had of mixing up the two. So it's very rare to sort of move. I've seen many examples in the United States, but in India it's very rare to move across both worlds. So that's, I'd always, when my students who are now professors, many of them, I keep telling them that this is something worth doing. And of course, here it works by either taking sabbaticals in companies, spending some time with them, or potentially doing a startup. But definitely getting some exposure to practice is very useful. And I always feel that it'll enrich their research. So that's something which I preach a lot. So talking about to younger people, I always say that I certainly have had some successes, but one has seen a lot of problems too, and failures also on the way. So I often feel that it's very important to be perseverance is very important. Perseverance is a very important quality. Very rarely do things work the first time or the second time. So to persevere is key to making something of your life, and that's one part of it. Another thing that I would also say is that most worthwhile things to do in life are always difficult. If it's worthwhile, I think for some reason it's always hard. So worthwhile things are difficult, and to do difficult things require a lot of work, and a lot of hard work too. And hard work is people only work hard if they like it. Unless you love your work, you don't work hard. It's difficult to work hard at it. So the question is, how do you find that thing that you love? And quite often in the United States now, young kids are always looking for something that they want to do, what they like. I somehow felt that when you're young, you may not really understand what these fields will become. So sometimes I say the best way of doing it is plunge into something and just work hard at something without knowing where it's going. But once you start working in it, you will get to like it. And that will drive the work that you require, and eventually will lead to success. So I will say, worthwhile things are hard things, you need to work hard at it. You've got to love your work. And the question is, how do you discover that? Often just jump into an area. You may not be quite sure what it is, but you'll probably, once you start doing well in it, you'll like it.
Thank you very much. Any other comments you'd like to make?
No, I would just say that I think we are, as engineers, and I'm an engineer, are in a really interesting phase of evolution. Many technologies have come, and certainly now we are moving into a new range of technology. I think wireless has been a very big piece, and it's still going to become bigger. But I'm fascinated by looking at AI. I was involved with it many years ago, and I sort of came back into it recently through some work I did with a small company. But I do feel that AI has gone through some ups and downs, but I think right now it's shown some amazing performance in some limited domains. But I do think that there's much more to be done there. And so I hope this time it's not a hype, but it's a long-term thrust, and it should, I think, support, add real value to everybody. It also comes, I think, with the problem of robbing jobs,
yes,
and killing jobs, and so society will have to react to it, and so I think it needs very careful management. Because we kind of, people need a meaning in life and need a job to sort of find that meaning, and how do we build a world where some of the functions are taken over by AI, but yet make life worthwhile living, requires, I think, not just engineers and scientists, but also people from humanities to figure something out. So, but we are certainly in a very interesting phase of life, and I think enormous opportunities.
Right. There's a convergence of capabilities happening as well.
Right.
So which can enhance the capabilities of AI and other areas.
And also I would say that almost if you look at how semiconductors have grown, or when wireless has grown, no one would have predicted the enormous growth and applications that has happened. So it is. The future always seems much bigger than we ever think, and so it is. So we are certainly in a very, very interesting phase on this earth, And I do think, and it's very evident that the world has to carry the entire population together. We can't, I think inequality is a major problem.
Yes.
And it's not, civilization as we know, it's not survivable with these inequalities.
Right.
So,
And to tackle some of the issues of survival of the
Right.
whole species.
right, I think so. I think, otherwise, people who get left behind will, I think, will disrupt the world. So we have many challenges.
Thank you
Thank you very much.
Professor
Thank you.
Paulraj.